In this module we will discuss the steady state sinusoidal response of the transmission lines. We introduced standing waves in the last module and we will continue with a brief summary of what the standing wave properties are. Standing waves are formed whenever a transmission line is terminated with gamma L that is not equal to 0. With gamma L equal to 0, we see that there is only incident wave. Whenever gamma L is not equal to 0, standing waves are formed on this terminated transmission line. We also found out what is the standing wave ratio in the previous class. We found that it is actually defined as the ratio of maximum phasor voltage to minimum phasor voltage on the transmission line, and maximum voltage is 1 plus mod gamma L. When the voltage actually reaches its maximum, the phase term goes to 0 or 2 pi, and the minimum voltage on the transmission line is 1 minus mod gamma L. This occurs when the voltage on the transmission line reaches its minima, and the ratio of these two is the standing wave ratio. And we actually also saw the relationship between SWR and gamma L. That is, given SWR, you can find out what is gamma L or magnitude of gamma L, or given magnitude of gamma L, one can find out what is SWR. At this point, probably one of the things that I want to specify is what is the range of this SWR. The range of standing wave ratio is between 1 to infinity. You can see that very clearly. When gamma L is equal to 0, standing wave ratio will be equal to 1. When magnitude of gamma L becomes 1, that is when it could be either open circuited load or a short circuited load, magnitude of gamma L becomes 1 and standing wave ratio goes off to infinity. In the same way, magnitude of reflection coefficient for passive transmission lines has to be between 0 to 1. 0 corresponding to no reflection, 1 corresponding to complete reflection. We also saw that on a transmission line there is voltage maxima and minima, and these maxima or minima repeat every lambda by 2, and the distance between a maxima and a minima, whether you are considering an open circuited load, short circuited load, or with gamma L something that is not equal to 1, the distance between maxima and minima is always equal to lambda by 4, where lambda is the operating wavelength related to frequency. The maximum magnitude will occur whenever the phase term goes to n pi. So you have 2 beta z plus phi L equals to n pi. Here please remember that n has to be negative, because your z is equal to 0 is located at the load point, and the input terminals of the transmission is located at z equal to minus L. So the line itself is there from z equal to 0 to z equal to minus L. Minima is located whenever the phase term goes to 2n plus 1 into pi. And this is something that I will leave as an exercise. It is just one step for you guys to show this. What is the impedance at voltage maxima? At the voltage maxima, we know that the voltage itself is some V0 plus into 1 plus mod gamma L. At that point, the current actually will be equal to V0 plus by Z0 into 1 minus mod gamma L. The ratio of these two will be seen to be as standing wave ratio into Z0, right? So the impedance at the voltage maxima is real and is given by SWR into Z0, okay, and at voltage minima the impedance is equal to, again it is real, but it is given by Z0 by SWR. I am assuming that Z0 itself is real, okay. You can show that these two as a simple exercise. Now this is something that you will also be able to easily show this. At any point on the transmission line, the impedance is given by Z0 into 1 plus magnitude of gamma L into e to the power j phi L plus 2 beta z. So this bracket had to be there for entire phi L plus 2 beta z. So let me just write down that bracket for you, okay. Here is a simple example for you guys to work out, okay. A transmission line is terminated in pure inductance, and a pure inductance, let us consider the value to be equal to jz0. This is pure inductance not because this is z0, it is because of this plus j thing, right, because the impedance of an inductor is j omega L. So for a given value of omega, we have chosen L such that the term product omega L will be equal to Z0. If your line is terminated with this pure inductance, okay, find the distance from the load to the nearest voltage maximum. The frequency is given to be 1 gigahertz and the phase velocity is given to be 0.67 c. What is this phase velocity in terms of c? It simply means that the medium that is filling up the conducting surfaces is not free space. If it was free space, then phase velocity up would have been equal to c. otherwise this is less than C. Okay, don't worry too much about what this particular thing means. We'll come back to this sometime later, okay, in a different module. Okay, the way to solve this problem would be to first find what is magnitude of gamma L. Actually, you are more interested in finding what is phi L also. So magnitude of gamma L will be equal to 1. I hope that this is obvious, because this is JZ0. You get gamma L as JZ0 minus Z0 by JZ0 plus 1 Z0, which is nothing but J minus 1 by J plus 1. The magnitude of that is equal to 1, but the phase is equal to pi by 2. If you are not convinced, I invite you to show this, okay, and then now you substitute this into the expression for maxima, right? So you want to find out where the maxima occurs. So you want to find this fellow. Phi L is pi by 2, so you transfer this pi by 2 onto the right hand side. So you have Z equal to 1 by 2 beta into 2n pi minus phi L. Substituting for all these results, you will see that the maxima is located at pi by beta into n minus 1 by 4, where n is an integer to be chosen such that this Z max is always negative. Okay. Now we also know the relationship between beta and omega, right? So omega by beta was equal to the phase velocity up, and omega itself is 2 pi into f, right, in terms of frequency. So you substitute that relationship into this one, you see that maximum can be written in terms of frequency and phase velocity up, and is given by up by 2f into n minus 1 by 4. The first maxima occurs when n is equal to 0, okay, at which point the location is minus up by 8f. Substituting for f of 1 gigahertz and up given here as 0.67 times the speed of light, you get maximum at minus 2.5 centimeter. Now here is a simple exercise. If you repeat this above calculation, except that line is now terminated in a pure capacitance. For a pure capacitance, this would be minus JZ0, and tell me what, or calculate for yourself when the first maximum occurs. Also calculate when the next maximum occurs. You can either calculate it by this expression putting n is equal to minus 1, or you can use the fact that maxima to maxima distance will always be equal to lambda by 2, and therefore you can use that one, right. So maxima are separated by lambda by 2. You can also find when the first minima occurs by again going to this lambda by 4 thing, right. Maxima to minima is lambda by 4. Now that we have seen enough about the circuit, let us actually look at the complete circuit analysis. Okay, this is important. Here we are going to consider the entire transmission line circuit, including the source and the load. Okay, so this is the complete circuit. You have a transmission line which has a certain length L, and then terminated by the load ZL. Okay, so it is terminated by load ZL. The load voltage is VL, the load current is IL. Now the idea is that what should be the load voltage, what should be this V0 plus. Okay, the answer is actually quite simple. The first thing you have to understand is that the generator at these terminals, right, this is called generator in an older terminology, or sometimes called as source. Okay, this generator has an internal impedance Zg, but to the input terminals of the transmission lines, the voltage is Vi and the current is II. Okay, so this is the voltage and current at the input terminals of the transmission line. Now here is a quick question. What is the impedance seen at this point? At the input terminals, what is the impedance seen at this point? The impedance will not be equal to ZL. That is obvious, because ZL transformed through a length L of the transmission line must be the input impedance that you see, right? We have seen the expressions for impedance on the transmission line. So the impedance seen here will be some Zi, and that Zi will depend on ZL and the length, right. So if you remember the formula, it was something like Z0 into Z0 plus JZL tan beta L, assuming real transmission line, or it would be tan hyperbolic gamma L divided by ZL plus JZ0 something, right. So that formula you need to remember, substitute into that formula the corresponding values of L and Z0, and then see that ZL gets transformed into Zi. So the generator only sees Zi, okay. And if you want to find out what is the line voltage, you know everything else. You can find out what is gamma L at the load, because you know ZL, you know Z0, okay. You can find out gamma L, you know what is gamma itself, therefore you can find out the phase factors E par plus gamma L or E par minus gamma L. What you don't know is V0 plus, which is the input incident voltage, right, or the incident voltage amplitude V0 plus. Okay. To calculate that, look at the equivalent circuit. The equivalent circuit will consist of a voltage divider with a generator and its impedance seeing Zi. The voltage at the input terminals of the transmission line is nothing but Zi by Zg plus Zi into Vg, but this voltage must be also the line voltage evaluated at Z equal to minus L. Please look at this expression very carefully. What we are saying here is that this voltage is nothing but the voltage on the transmission line as you come towards the source side or the generator side, and at Z equal to minus L is where the transmission line is located. That voltage must exactly be equal to the input voltage on the transmission line, right. Now you can substitute for Z equal to minus L, okay, on the line voltage of the transmission line, and you will see that this is the expression. If you now combine these two expressions, right, and call this as Vi, you can immediately see that V0 plus is given by Vi by e power minus gamma L plus gamma L into e power gamma L. Okay. If the line is lossless, then you replace gamma by j beta and then write down what is V0 plus. V0 plus in this particular case can turn out to be complex. Okay. Now if I know what is V0 plus, it is a simple matter to find out what is load voltage. Why? Because load voltage has to be evaluated at Z equal to 0. When you put Z equal to 0, you will see that this term will be 1, this term will also be equal to 1, and this is 1 plus gamma L times V0 plus. This is the load voltage. Let us actually look at an example here. Suppose we have a lossless transmission line with characteristic impedance of 50 ohms, okay, and the length lambda by 4, connecting the source which is given by 10 cos omega t plus 30 degrees, okay, and having a generator impedance of 25 ohms, and this is connected to a 100 ohm load. So the load is real, the generator impedance is real, the characteristic impedance is also real, the length of the transmission line is given by lambda by 4. Find out what is the load voltage. Well, first convert this 10 cos omega t plus 30 degrees into a phasor form. So if you convert that to phasor form, you get Vg as 10 e power j 30 degrees. Okay. So this would be the generator voltage. Find out Zi. Okay. If you remember this case that we considered when beta L was equal to pi by 2, which essentially means that L should be lambda by 4, we saw that the input impedance has a simple form which is given by Z0 square by ZL. What is Z0 square here? 2500. What is ZL? 100. So the ratio of these two will be 25 ohms. So this is the input impedance. If you are not following this one, you can substitute the expressions for L, okay, Z0 into the impedance formula and find out that this is actually 25 ohms, okay, and therefore the input voltage will be a voltage divider between 25 and 50 ohms. So 25 by 50 plus 25, which is 25 by 25 plus 25, this is Zg is 25. So one half of the generator voltage appears at the input terminals of the transmission line, which is 5 e power j 30 volts. Now you can also find out gamma L. How will you find gamma L? You know the load voltage which is 100, you know the characteristic impedance 50, so 100 minus 50 by 100 plus 50, 50 by 150, which is nothing but 1 by 3. Gamma L is also real. Now you substitute all these expressions into this one, right? So V0 plus is nothing but Vi. You already have calculated what is Vi. You know what is gamma. Gamma is j into beta, right? So you substitute that. Gamma L is 1 by 3. You can substitute, find out all these values, and then you will see that V0 plus is 7.5 volts, okay, but lagging by a phase angle of 60 degrees, whereas the input voltage is 5 volts leading by 30 degrees. The phase difference between input voltage and V0 plus itself can be found out, and this is around 90 degrees. Same thing, the load voltage will also be equal to 10 into e power minus j 60 degrees. So you can actually see that the load voltage magnitude is the same as the generator voltage, except that these two are now lagging by 90 degrees, right? So one voltage, the generator voltage is leading by 30, this fellow is lagging by minus 60, so the phase difference between them is 90 degrees, okay. Here is a simple exercise. I would suggest that you do this exercise. You interchange the source and load impedances, okay, and then find out what is the load voltage. We will consider a more common situation where one transmission line actually gets terminated by another transmission line. Okay, in fact many times one gets terminated by second gets terminated by 3 of different lengths and different characteristic impedances, because you are trying to do some matching concept that we will see later in a different module. What we are interested is how much voltage actually gets reflected from the first transmission line, how much voltage gets transmitted into the second transmission line. Okay, to do so you just need to invoke KVL and KCL. Very simple. Let the incident voltage on the first transmission line have an amplitude of V01 plus, and the reflected voltage because of the load at Z equal to 0 be V01 minus. So the line voltage on the first transmission line of characteristic impedance Z01 will be V01 plus V01 minus from this side, and from the right side, that is from the second transmission line, you only have V02 plus. What happened to V02 minus? Well, the transmission line is continuing towards infinity, therefore there is no possibility of having a reflected voltage on the second line. Okay, so therefore right side voltage is just V02 plus. So V01 plus V01 minus must be equal to V02 plus. Now with KCL you will see that the total line current here is I01 plus I01 minus, okay, incident and reflected currents, plus there is some current through the load itself which is IL, plus some current going on to the second transmission line. Again there is only forward going current I02 plus. Okay, you can equate this, substitute for I01 plus and I01 minus in terms of V01 plus and V01 minus. Also note that the load current IL is given by V02 plus divided by ZL, which is correct because V02 plus is the voltage on the second transmission line, but that voltage at Z equal to 0 is precisely the voltage across the load impedance. In fact that is also equal to V01 plus by V01 minus, but this one will give us easier answer. So I am writing IL as V02 plus by ZL at Z equal to 0. So I hope that you guys are convinced about these equations. If you are convinced, substitute I01 plus and I02 minus in terms of all this V01 plus and V02 minus, and you can see that the ratio of transmitted voltage onto the second transmission line to the incident voltage from the first transmission line, which we will call as the transmission coefficient. This was very similar to an interface plane wave coming in and some transmitted voltage, right, or a transmitted electric field, that is given by 2 Z parallel by Z parallel plus Z01, and the reflection coefficient gamma L is given by, which is the ratio of reflected line voltage and reflected voltage on line 1 to incident voltage on line 1, given by Z parallel minus Z01 by Z parallel plus Z01. But what is this Z parallel? You can actually substitute all this and find that Z parallel is nothing but the equivalent impedance, the parallel combination of characteristic impedance Z02 with the load ZL. Okay, so this parallel combination will be the effective impedance that you are going to see, the first line actually going to see, and you can use that effective impedance to calculate transmission and reflection coefficient. There is last thing about power relationship. There is what I feel is undue emphasis placed on power relationships. Well, at this point all you need to remember is that average power in terms of phasors is given by half real part of VI I conjugate or V into I conjugate. So the average power delivered by the source to the input terminals of the transmission line will be, I forgot a half here, but please do keep that half in mind. So this is real part, half real part of VI I conjugate. Okay, we have already seen what is VI. VI is nothing but this particular thing, right? So VI is Zi by Zg plus Zi into Vg. So given Vg, find out what is Zi, the input impedance of a length transmission line of length L, and then write down this as half real part of VI I conjugate. Okay, the average power dissipated by the load is half real part of VL into IL conjugate, and this occurs at Z equal to 0 because that's where we have actually kept the load. If the transmission line in between is lossless, whatever the input power, average input power that is given to the input terminals of the transmission line will exactly be the one that is delivered across the load. Okay, so there is no loss out there. In this expression, if you want to find out how to find V0 plus, okay, this is the same cascaded transmission line experiment case that I am showing. except that the load has been moved to the second transmission line. Now the analysis is very simple, you can do KCL, KVL and all, but the idea is to actually transform the load. Okay, first consider ZL, which is the load connected to the second transmission line, but the second transmission line has a length L2. Therefore, the impedance seen looking at these terminals, right, at the output terminals of the first transmission line will be ZL transformed through a length L2 with characteristic impedance Z02, call that as some Zi2, okay, and that Zi2 further gets transformed to Zi1 via length L1 on the first transmission line. So now you get the effective impedance seen from the two transmission lines. This is the effective input impedance. This forms a voltage divider with the given generator impedance Zg, and you can find out what is V0 plus by following the same logic. In this module we will discuss Smith chart, one of the most widely used graphical tool, and before the advent of personal computers this was probably the only way in which microwave and RF antennas problems were solved. And the principal use of Smith chart is to solve several transmission line problems. You can actually use Smith chart to find impedance at a point on a transmission line. You can find out the reflection coefficient at any point on the transmission line away from the load. You can design matching networks. You can determine the standing wave ratios. You can determine where the maximum occurs, where the minimum occurs. All these things could be done by Smith chart, and Smith chart was the most popular tool, a graphical tool especially, for doing all these problems, okay, before PCs arrived. And now you can actually use ready-made programs, or you can write simple programs for yourself to manipulate the equations to solve all the problems that a Smith chart does. So in this case the question might be that why are we studying Smith chart, right? The answer is that for a first design, okay, especially when your lines are lossless, you can actually use Smith chart to get reasonably accurate results, and moreover this Smith chart gives you a qualitative understanding. Okay, so the Smith chart is something that gives you qualitative understanding of the problems before you actually can plug in to get the quantitative numbers. Moreover, Smith chart is such a nice graphical tool that most RF engineers and microwave engineers or even antenna engineers visualize most of the problems via Smith chart. Therefore, learning Smith chart is something that will be very valuable for you when you decide to pursue RF or microwave engineering. Now, what exactly is a Smith chart? Smith chart is fairly simple, okay, to define what it is. It is actually a graphical plot of normalized resistance and normalized reactance functions in the reflection coefficient plane. Okay, there are several subtleties involved here. Let us take it up one by one. What do we mean by normalized resistance and reactances? What we mean is that impedance Z, if you divide that impedance with respect to the characteristic impedance of the transmission line, then that forms the normalized impedance. If the characteristic line that you are considering, if the characteristic impedance is real, which is what you would mostly consider, then if you have the load resistance, then that load resistance divided by the characteristic resistance will be the normalized resistance. Load reactance divided by, or load reactance normalized to the characteristic impedance will be the normalized reactance. So any load in the problem that you are considering can be normalized with respect to the characteristic impedance of the transmission line, okay, and that is what we mean by normalized resistance and reactance, in general normalized impedance. This normalized impedance, okay, is plotted in a reflection coefficient plane. Why is reflection coefficient plotted in a plane, or why is reflection coefficient even considered to be plottable in a plane? If you remember, reflection coefficient is not always a real quantity. It is defined by ZL and Z0 and given by ZL minus Z0 by ZL plus Z0, and when your load impedance happens to be complex, then your reflection coefficient will also be complex. Okay, so a complex reflection coefficient can be plotted as a point in a complex plane with real axis giving you the real part of gamma L and the y axis giving you the imaginary part of gamma L. Therefore, every point on the reflection coefficient plane will correspond to a particular gamma L and hence correspond to a particular ZL. Okay, and if you normalize that ZL, there is a one-to-one correspondence between the two very nicely, okay, and normalization is done so that numerically everything is manageable, otherwise you can work with unnormalized resistances and impedances as well, okay. So on the reflection coefficient plane, every point corresponds to gamma L, and every such gamma L corresponds to a given load impedance. And here is a picture of a person who invented Smith chart called Philip Smith, and he's written a very nice book on how to use Smith chart. If you can get hold of that book, it's very valuable to read that one. Okay, this is how a Smith chart would actually look. Okay, a Smith chart is basically collection of circles. Some of these circles are called as constant resistance circles, some of the other circles are called as constant reactance circles. Now reactance could be positive or negative. Positive reactances correspond to inductance, negative reactances correspond to capacitance, okay. So you can have constant positive reactances or constant negative reactances, okay. If you look closely at a Smith chart, you will actually see that they are actually labeled here as constant resistance or conductance circles, okay. Resistance and conductance are interchangeable in some sense, in the sense that resistance is a real quantity, conductance is also a real quantity. This chart can be split into two parts. The upper hemisphere consists of positive reactances, okay, and lower hemisphere consists of negative reactances, okay. If the Smith chart is being used for impedance plotting, so the circles are constant resistance circles, upper half is the inductance plane, the lower half is the capacitance plane. If you are using this as an admittance chart, then the circles are constant conductance circles, okay, because on an admittance or in a parallel one talks about conductance and susceptances. So this would be the capacitive susceptances and this would be the inductive susceptances when the chart is being used as an admittance chart. These are some of the circles which I have marked. These are constant R circles. You can actually see that the circle with the largest diameter actually corresponds to R equal to 0, okay, and then you keep increasing R, okay. So this circle which is almost at the center is R equal to 1 circle, okay. The normalized impedance is equal to 1 here, the normalized resistance is equal to 1 here, okay. These values of circles are for increasing values of R, okay, as R equal to 0, R equal to say 0.3, 0.5, and then eventually coming to R equal to 1, R equal to 2 or R equal to 3, I believe this one, and then keeps increasing. And these circles which you cannot really see are for really large values of R. Typically you don't really work in those regions, okay. So clearly this would correspond to the short circuit, this would correspond to the open circuit. These are some of the constant reactance circles that you can see. The circle at the center is actually looking more like a straight line, okay, which has a radius of infinity, corresponds to 0 reactance. All these circles in the upper hemisphere correspond to inductance if the Smith chart is impedance chart, and all these circles correspond to, these are rather semicircles, these circles correspond to capacitive reactances when the Smith chart is considered as a impedance chart. Here is a short derivation of Smith chart. First of all, we denote by this small ZL the normalization of the load impedance with the real characteristic impedance. The characteristic impedance is Z0, but when the line is lossless and the characteristic impedance is real, you can write this as R0, indicating that this is only resistance, okay. So ZL in general is RL plus JXL, can be normalized, and these normalized values are written as R plus JX. Now look at gamma, the reflection coefficient. Gamma is nothing but ZL minus R0 by ZL plus R0. This can also be written in terms of the real part of gamma and imaginary part of gamma, because gamma is a complex number. Now substituting for ZL after normalization will give you ZL minus 1 by ZL plus 1. You can invert this relationship to write ZL in terms of gamma also, okay, and then write down ZL as R plus JX, right. This ZL is R plus JX, and then you replace this magnitude gamma e power j theta gamma, which is the phase angle, by gamma itself, and gamma can be written as gamma R plus j gamma I, and then you can use complex number normalization to do this thing and find out that this is given by this, and R will be the real part of this one, given by 1 minus gamma R square minus gamma I square by this thing, and X, which is the reactance part normalized, is given by 2 gamma I by 1 minus gamma R square plus gamma I square. What you have to see from this boxed equation is that no matter what gamma r and gamma I consider, which would be a point on the reflection coefficient plane, there will be a corresponding r and a corresponding x. Sometimes you might consider gamma r and gamma I which is unrealistic, say gamma r is equal to 100, gamma I is equal to 50, and then the magnitude of gamma will be greater than 1, which is unphysical for a passive transmission line. There will be corresponding r and x, but they won't be completely meaningless physically. So you have to understand that the magnitude of gamma will always have to be less than 1, and therefore you are not considering the entire gamma plane but only a restricted gamma plane. What are the properties of constant r circles? These gamma r minus, so if you actually look at this equation and then rearrange the equation, see that the equation can be rearranged in the form of a circle equation where the centers are given by r by 1 plus r comma 0. This is on the horizontal line, right? So on the horizontal line the centers are given by r by 1 plus r and 0, and the radius of these circles are given by 1 by 1 plus r. The centers all lie on the gamma r axis, right? On the horizontal axis gamma is gamma r. So all the centers for all r circles will lie on gamma r axis, okay? And the special case with the largest radius is when r is equal to 0, the radius is equal to 1, okay? That center is given by r equal to 0 is given by 0 comma 0, okay, and this is centered at the origin, has the largest radius. What you have to observe is that as r starts to increase, the radius starts to decrease because 1 by 1 plus r starts to decrease. Moreover, the centers start moving towards the right side, right, because what is happening, r is increasing. Eventually when r is equal to infinity, the radius will be 0 and r equal to infinity corresponds to open circuit. What would be the center there? Center will be 1 comma 0. Therefore, all of the centers for the constant r circles are located between origin and 1 comma 0 on the real axis. Moreover, this is very crucial, all the r circles pass through the gamma r equal to 1, gamma I equal to 0 point, which is the open circuit point, right? So if you are not convinced, you can take a look at the constant r circles. Every circle is passing through this right side point where gamma r is equal to 1 and gamma I is equal to 0 corresponding to open circuit. This outer circle is the one which is r equal to 0, has the largest radius, okay. Similarly, if you look at the constant x circles, the center of these x circles are at 1 comma 1 by x, the radius is 1 by x. Now at x equal to 0, the center will obviously be at 1 comma infinity, right. So on the y axis the center is lying at 1 comma infinity. What is the radius of this one? The radius of this is 1 by x equal to 0, so the radius is infinity. So you have the center at 1 comma infinity and the radius of infinity, which is actually a straight line, okay. The centers of all other x circles will lie on the gamma r equal to 1 line, the centers will be on the y axis, and for inductive reactances the centers lie above the gamma r axis, and for capacitive reactances they would all lie below the gamma r axis. Further, x equal to 0 circle is the gamma r axis because, as I just said, x equal to 0 corresponds to radius of infinity, which means that it is a straight line, and the center is at 1 comma infinity, okay. The x circles again become progressively small as magnitude of x increases from 0 towards infinity. At infinity point the radius is 0 and the center will be at 1 comma 0, and all the x circles pass through the right side point. So this right point, the point out here, is very interesting because every circle, constant reactance circle as well as constant resistance circle, all of them pass through this particular point, okay. So this is all about Smith chart. Now we will end this module by looking at some of the impedances that are plotted on the Smith chart, okay. So I have shown enough points on the Smith chart. What I would suggest is every point you try to locate on the Smith chart. You can get hold of a Smith chart in a store, you know, in a place where you can actually get that one, and use that Smith chart, okay. This Smith chart does not show all the circles, this is just for the clarity, but the Smith chart that you will get will have a lot of circles, but you take a pen or a pencil and then start marking every point here, okay. Or you can print out this slide and then cover up all these points A to L, okay, A to M, N, actually you can cover up all these points and then try to see whether you are actually getting these values of A correctly, okay. For example, what is the impedance at point A? You have to see that this is at the meeting point or the intersection of the constant R and a constant gamma circle, right. What is the constant R circle here? The constant R circle is 1, constant reactance circle is 1. So A is at 1 plus J1, and that is precisely what you get. What about D? D is at 0.2 plus J0.2. What about C? C is at R equal to 0, X is equal to 0. So C will be equal to 0 plus J0. What about B? B will be at 1, right, real R is equal to 1, and for X this is 1, but this is at the lower hemisphere, therefore you have to mentally add a minus 1 here. So this B will be 1 minus J1, as you can see here. Okay. What about M? M will actually be slightly higher than 0.5, because if you actually draw a circle out here, it will be slightly greater than 0.5, although it is not shown. Okay. So this would be say 0.6, and then on the X reactance this is at 2. So this is 0.6 minus J2. Okay. So this is the value of M. Anything else that is interesting you can find out. For example, what is F? F is not shown to lie on any of these points, so you have to interpolate slightly, right. On the constant R circle this is 0.2, but for the impedance this is lying between 1 and 2. So mentally if you try and interpolate this one, this might turn out to be around 1.2. So this would be 0.2 plus J1.2. Okay. So this is how you would try to find. Point I, of course, being open circuit, is given by infinity, right, and for X this would be equal to 0. In the next module we will actually start using Smith chart for various applications as we said, and we will take up from that one. Thank you.